we expect quite amazing new ways of doing compute with quantum computers. So we might be able to solve problems we were not able to solve in the past, which also means that we find new ways of thinking of problems, and maybe going in areas which we deliberately have not touched for the past 100 years or so. Because now we suddenly can, or at least on the horizon, we can see that we may be able to do that in future. So we have chosen to share with you three use cases. And for the first one, we're going quite far up in the sky, looking at the mission planning for satellites, because satellites do not just go on one orbit forever, but they are actually steered to go somewhere and to do whatever they're designed for. And however, steering them is way more expensive than this is, for example, for a car on the ground. And hence, even very small improvements bring a lot of benefit. From there, we are collecting data, and this data needs to be analyzed. And this becomes our second use case. And our third use case is actually a fairly classic one, and looking at aerodynamic simulations and how doing them different may open a new horizon. But with that, I would hand over to Vincent on space mission optimization.
So I am Vincent Baudoui. I work for Airbus. And with this part of the talk, you will learn more about the space mission optimization use case, which is the problem of scheduling acquisition on an Earth observation satellite, and what are the ways using quantum computing can help solving this problem. So it's a use case on which we're working at Airbus and within the equality project with our partners from Pascal, Capgemini, and INRIA. So this is the description of our space mission optimization problem. So we are talking about a Earth observation satellite which is orbiting the Earth. So the satellite is revolving around the Earth, and it will take photos of the Earth surface here and there. So we have many requests from different users requesting to acquire an image of a given area of interest. And so the satellite revolves on its own orbit. So this is fixed. It's something we cannot change. But the satellite is agile, meaning that it can be oriented towards a given target or the other when it's revolving around its orbit. And here comes the problem of scheduling the proper acquisitions to be made by a satellite during an orbit, so that we try to maximize the number of images taken among the requests from our users. So you see a nice photo, a nice simulation on the left of the satellite and the different regions we want to acquire in white. You can see we can acquire very small regions or larger areas in several passes. But we can describe with the scheme in the middle our problem with a different set of various acquisition requests deposited by our customers, and then each request is available for imaging during a given visibility time window during the orbit of the satellite. So it's a time constraint. And then the mission planning problem is to select some of the requests to be actually imaged by the satellite, knowing that the satellite will not be able to take all the images requested because it has to maneuver and point towards one image and the other. So we need to take into account maneuver time between two acquisitions, and hence we have to choose the best possible path among all of those requests. So we will have some requests that are fulfilled and some requests that we will not be able to fulfill during this orbit. So that will be taken during a future orbit. And on the right, we can describe the same problem with a kind of Gantt chart. So going through time, we have, like, for instance, 4 different requests from customers. Each of them is available during a given time window, which is depicted with the color bars. And then we can say, okay, the satellite will first acquire the first image of request 1. So it will take some time to acquire the image. It's the black line. And then it will maneuver, it's the dotted line, towards request 2, take some time to image it, and then maneuver towards request 3. But then it will not have enough time to take that image. So that will be it for this problem. We'll only be able to acquire 2 images among the 4 requests that we had. And possibly if we had done that in a different order, maybe going towards request 4 before would allow to acquire it. So we'll get 1 more image. And as Moriz was saying at the beginning, if we are able to acquire 1 more image per orbit, as the satellite is orbiting every day several times around the Earth, it can add up to a large amount of increase of the number of images we can acquire. So that's a very interesting problem. So it's a complex combinatorial optimization problem that we have to solve. And that's why we proposed to study it within the Equality project to see what quantum computers and quantum computing could bring to this kind of combinatorial optimization problem. And see how we can go for the future. So the aim of the project here is to look at algorithms and methods to actually be able to solve it with the current existing quantum computers, and also preparing the future when the quantum computers become larger and more efficient, so that we can plan the future for this kind of problems. We had a previous study using quantum computing that was done with a D-Wave quantum annealer in 2021, and you have the name of the paper at the bottom if you want to have more information about the problem itself and how it was solved with this approach. From Airbus, within the Equality project, we're providing various test scenarios of the space optimization problem. So it's the test data that was used in the previous study as well. So we will be able to compare them to the current study and the results that we will get. So it's 720 test scenarios with various problem sizes and complexity. We have 2 examples on the right. So on the right, we have the 2 pictures. We have the line is the orbit of the satellite passing over an area on the Earth. And then the rectangles are imaging requests from customers. So on the scenario on the left, we can see that we can have very spread out requests, imaging requests. So the satellite will be able to acquire almost all of them. So we have a few conflicts between requests that are very nearby next to each other, but more or less it's an easy problem because it's easy to acquire and to maneuver between all the requests. While on the scenario on the right, you can see that all the requests are clustered in the same area, and here we have a lot of conflicts and decisions to make in order to know which image will be taken or not, in order to try to maximize the number of images acquired, respecting the maneuver between all the images that we take. So it's quite small scenarios. Here we have a few dozen of requests, while in a real operational scenario, it's way bigger problems. But here, of course, as we want to solve them with the existing quantum computing, which have currently a limited size, that's why we use fairly small scenarios, but still they are quite realistic, and they show the kind of problems that we have in reality, and so that the results we can get on such small scenarios will be very interesting and provide insight for the future when we can solve larger instances. So what we want to do here is to compare various quantum computing approaches and compare them also to the classical optimization results that we can currently have with the classical computers. And so we will look at various info, such as the optimality of the solutions. So here, the number of images we are able to acquire in a given orbit. As I was saying, that's a very important thing. But we will also look at computation time because as we are in an industrial context, the computation time allowed to solving this mission planning problem is quite limited. We only have a few minutes before the mission plan is sent to the satellite so that it starts acquiring images. So that's a very also important constraint, and we want to see how well quantum computers perform or will be able to perform in the future. And so the last one is the scalability, because of course we will get larger and larger problems with more and more acquisition requests in the problem. And so we want to see what kind of advantage quantum computing could bring when the problem scales up. So we can go to the next slide to see the different approaches that we are considering within the Equality project. So it was very interesting to discuss with all the partners, the quantum computer experts, and ourselves with the test case. So we have discussed and chose to consider three different approaches, three different algorithms that could be used to tackle this problem. So the first one is a standard algorithm, quantum algorithm, to solve optimization problems. So it's called QAOA, so it's Quantum Approximate Optimization Algorithm. It's a hybrid algorithm using either both classical and quantum computing to find an approximate solution to a combinatorial optimization problem. So briefly speaking, we have a quantum circuit that is encoding the problem, and it's parametric. So it has different layers. We can choose the number of layers defined in this quantum circuit, and its parameters then are optimized with a classical optimization loop. It's optimized iteratively. So iteratively, we evaluate the quantum circuit and then optimize its parameter, updates its parameters with the classical optimization loop. And this, by this iterative solving, will lead towards a good, close to optimal solution. So that's the general idea of this approach. For that, we redefined our problem as a QAOA, so quadratic unconstrained binary optimization problem. It's a standard formulation, just linearizing and adding the constraints that we had in the problem to the objective function to have this kind of quadratic optimization problem that could be then handled and coded in this QAOA, the quantum circuit of the QAOA. And this was done using the Pulsar library from Pascal. And we have run various tests with this approach, but it did not prove to be very efficient with the current computers. It was only on simulations here. So it was not very efficient because it was not able to find very good solution. Of course, it's an approximate approach, so we will not find the optimal solution. But the solution quality was a bit lower than what we would expect. And also for the simulation, it was not very scalable because even for our small test cases, the largest one, it was not able to solve them. So that's why we decided to pause this approach for now and study other more interesting approaches. But of course, this kind of approach could definitely be very interesting when the quantum computer size increases, so it could be still a very interesting approach because it's very generic and could be applied to various problems in the future. So the second approach we studied was a custom graph algorithm designed by our colleagues from INRIA. So we model the problem as a graph where each node represents the orientation of the satellite at a given time step. So meaning that the satellite will point towards a given target that it wants to acquire. And then we have edges between the nodes if a maneuver is feasible between the two nodes. So meaning that if I have one node where the satellite is acquiring a target, I can have an edge if it can maneuver towards acquiring a second target represented by the second node. So that's a graph that we can build. So it's a graph representation, and we can use graph exploration algorithm that will find the best path in this kind of graph. So the path that goes through as many nodes as possible, meaning that we will acquire as many images as possible. So it's a classical algorithm, we are running tests on our test scenario to see how well it behaves. For now, it doesn't look to be very scalable, so it's okay for the kind of problems that we are considering here. But if we want to go in the future to larger problems, it could be limited at some point. And also, we want to study a quantum counterpart, or to see how quantum computing could also help this kind of graph exploration algorithm to be more efficient. But still, it's also what is very interesting in this kind of project. We are studying quantum computing approaches, but it can also bring up new classical computing solutions, such as this graph algorithm, because we are discussing about the problem and trying to model it different ways. So that's also very interesting to have this kind of discussion, even for classical approaches that could also become helped by quantum computing in the future. And the last and third approach, which is the most interesting for now, is based on maximum independent set formulation. So it's also a graph formulation of the problem, but the graph is different from the one we were discussing before. So here, each node represents the acquisition of a target at a given time step, so that's similar. But then the edges, instead of representing feasible maneuvers between two acquisitions, they represent infeasible maneuvers. So if I do not have enough time to take both target 1 and target 2 at their given time step, then I will have an edge between node of target 1 and node of target 2. And with this representation, my problem becomes finding the maximum independent set in the graph. So an independent set is the set of nodes that are not connected to each other. So we want to find nodes with no edge between them. So meaning that we do not have any infeasible maneuver between those nodes. So it means that maneuvers are feasible between those nodes. And we want to find the maximum such set so that we acquire a maximum of images. And so that's a very interesting formulation, because current quantum computers are very efficient to solve these kind of problems with quantum adiabatic annealing. Especially, so it's limited to unit disk graphs. So it's a specific type of graphs where nodes that are connected to each other are not too far from each other. So nodes with edges are close to each other when we lay out the graph on a 2D map. And so, really, quantum computers could bring a good advantage on solving this kind of problems. And so that's why we are currently testing this approach using a custom library encoded by Pascal. So it's a maximum independent set library. So it provides a greedy approach where it takes a large graph of our problem and then divide it into different subgraphs that are unit disk graphs, and on each subgraph we can solve this maximum independent set problem using, for instance, a quantum computer, or if the graph is sufficiently small, a standard approach. And then gathering all those results, we are able to get very good solutions. So it's providing for now in simulation very promising results, and we are looking forward to execute it on an actual quantum computer during the summer. So that's very exciting news for us, and yeah, we are looking forward those results. So that was it for the space mission optimization problem.
So let's start. Also from my side, a warm welcome. I'm also working at Airbus in the space section. So as you've learned from Vincent's use case, Airbus is also beside the planes active in the satellite business. And we're providing satellites, of course, and ground segments, and also the services of processing those data. An important area of this section is, or of this business is Earth observation, as you have learned. And Vincent has told you about optical systems, which are one important pillar, but another one is a radar system. So for Earth observation, radar systems are very important since they are independent from daylight. So you can take 24/7 pictures of the Earth, and mostly of weather conditions. So only very bad weather can hinder the data recording a bit, but mainly you can look through clouds and even through the canopy of forests, if you like. So what we are doing is we sending out a radar wave, which is basically a microwave, and collecting the echo. So within this wave, or within the recorded echo, there's information about the surface of the Earth. So in order to extract it, you need to process it, because the problem is, which we can see on the first slide with some content, if you switch to it, that the data depends on the recording, and the recording is used a very certain principle, because the main problem is that the resolution of your image depends inversely on the antenna length. So the longer the antenna, the better the resolution you've got. So for an airborne or spaceborne system, it would mean we need like hundreds of meters of antenna length, which is not a good thing for a space system to have. So what we do is a trick. So we are not sending out a single pulse, radar pulse, but thousands of them, and moving along a track, and then recalculate all this send out pulses and collected echoes in order to be one antenna. So which is called Synthetic Aperture Radar. So this is a synthetic aperture in this case. So as you can imagine, you've got a very complex echo pattern, and you see it on the right picture. The lower picture represents the process data, which means this is a single reflection on Earth. So if this is an artificial data set, of course, because mostly you don't have only a single reflection. But if you only have a single reflection on Earth, it would be represented like this cross shape, down, right. And in the raw data, so the collection of all the echoes, you would see with your satellite or with your sensor, it would be an interference pattern of all these echoes you've collected. So which makes it a very complex problem to be processed. And since the resolution is getting better and better, and the data is getting bigger and bigger, it's actually becoming a supercomputing problem. So not real supercomputing in sense of we're using millions of cores, but at least we are using thousands of cores. So we have got a HPC application where we came up with the idea somehow might quantum computers solve this more efficiently, or is there a spot for quantum computers or quantum algorithms to be superior to the classical approaches? So what you're basically doing is we've investigated together with University Leiden, so colleagues from University Leiden in our subcase project included. So we've brainstormed a bit about this problem and came up with the idea that these interference patterns look very promising for a machine learning or a classical machine learning network to be recognized, but it certainly does not work out for more complex patterns. So if you go to the next slide, you see a real image on the right below side and the corresponding raw data. So what you see is your interference pattern is becoming much more complex. So it basically looks like white noise. And I'm always amazed how out of this noise can be by purely process it to with I call it magic into a human readable image. So it's always amazing to see it. So the idea is that this might not be feasible for a classical algorithm to be recognized somehow, but at least parts of the data processing shows promising approaches for quantum computing, because one important part of this processing in the classical sense is you need to interpolate your data set. It's called stalled interpolation, and then do a Fourier transformation. So a Fourier transform and the stalled interpolation together can be expressed by a non-uniform Fourier transform, which is called NUFT in that case. And there's a connection between parametrized quantum circuits because they have their naturally shape of it and the expectation value have a good inductive bias for this kind of problem, that there is a connection between this non-uniform discrete Fourier transforms or Fourier transforms and this quantum circuits, PQCs. So that was the main goal of the research of the colleagues at University Leiden, and they found actually a good solution for it. So if you go to the next slide, the basic idea is here you see on the right side the processing scheme you have in a classical approach. Then on the right side of the diagram, you see this non-uniform Fourier transform approach, which is still classical, but it's not widely used in SAR processing right now because the non-uniform Fourier transform are quite computing intensive. So it's faster to have a stalled interpolation in a FFT than doing a non-uniform Fourier transform. So what we are planning is to cut the processing at this point and do a classification process for the QML there. So the colleagues of University Leiden has found two possible solutions for this kind of problem because of this very good inductive bias. So what we are doing now is probing those results. So going to the summary slide, the last one. We are probing this right now with artificial data sets, of course, because it's very hard to have real data sets in place for machine learning purpose, but we can do it for very simple, very small problem sizes with simulator, and then adding complexity, adding distortion, for instance, moving targets, adding multiple targets, and probing our two approaches. So, and once we find out that this is a feasible solution, then we might have a really quantum superiority about classical processing, and even find more possible use cases for it. So not replacing parts of the processing as a quantum computing accelerator, for instance, but also having a look very directly into the raw data and finding out before processing, is it worth to be processed at all? So recognize pattern in the raw data itself. So that's the basic idea, and with that I thank you for your attention.
I would then maybe go to the next topic directly. The last one, which is maybe one where the brand Airbus is a bit better known for, aerodynamic simulations. And I just quickly wanted to go give credit to Albana Topi and Luis de Vega, who formed this presentation, but cannot be here today for very good reasons, so I will step in. And let me first describe the part which has nothing to do with quantum, but with the way we have done simulations since decades now. And basically, the way forward is simple. You start with some kind of a shape, which you have. It may be an airplane, it may be just a component, it may be something different, whatever. Everything is flying if you put enough thrust on it. And then you create a mesh around it. And then afterwards, you use a CFD solver, which is typically based on some finite volume scheme, and you get a resulting flow field. And that's actually very intuitive, because what you're looking at is the local behavior around your mesh cells, around your grid. And from that, overall, the solver will result in a global solution, and all kinds of properties like lift and so on, what you need for flying. And these finite volume schemes are basically the workhorse of aerodynamics today. Yes, they work really very, very well. And today there is not really a relevant solution left that cannot be predicted properly. Yeah, so it's very well understood, very suitable for all kinds of purposes. And we know just everything is working fine. So why changing? Yeah. First thing, maybe just to note before we go to the why, is that even though it's definitely good enough for all the purposes we have, it's not arbitrarily accurate. Yeah. So of course we are bound to the size of the cells, which are getting very, very small in the area where the flow field is getting rather complex. Yeah. So the CFL condition and so on. So after a while, you notice the amount of compute you need is getting very big due to that. Yeah. So because you have very many cells, a lot of compute, and even worse, you need a lot of memory, because for each of the cells, you have to store all the properties. And that is, especially for today's hardware and for hardware we foresee for the future, getting more and more difficult, because we're getting more and more cores and more compute. But memory is getting fairly expensive, and where that the computations are getting expensive, and when you want to optimize in very complex situations and very wide situations, then this is becoming expensive. So the question is a bit: are finite volume schemes, so however good they are today and however suitable they are today, are they future proof when we're scaling further and getting better? And there is an alternative approach, right? And a very promising approach. And this is working entirely different. So it is based basically, yeah, you start also with a shape at some point, but then the flow field is represented by a neural network, so-called physics-informed neural network, or theory-trained neural network. And this is based on the underlying PDE. Yeah? And the nice thing about that is that you feed it, of course, with data from a flow field. Yeah? And this can be data you generate from the PDE, but it can also be data which is, for example, measured, coming from different sources, yeah? Which, of course, you have very often, because after you design something, you fly it and you have a lot of measured data. But the whole flow field is inside the neural network, so stored with relatively few, so still these need to be very big neural network, but still start with relatively few parameters. And this makes it fairly good, fairly memory friendly. And if this approach is working, then it is actually looking quite future proof. So is it better than a finite volume scheme in the end? Well, the thing is, we have limited accuracy here in the mesh. Here we have a continuous flow, but we have limited parameters here in the function. So we're a bit looking from limits from a different size. And in theory, it scales perfectly. You could even go for Navier-Stokes, but especially if we enhance with quantum algorithms, because this is where this is perfectly suitable, because we have basically a target function with a lot of different combinations of states we need to adjust. This is the idea of a neural network. And so looking at this problem in the context of equality is actually quite promising and also quite meaningful for the future. However, how do we start? Yeah. So when we started with finite volume schemes, we didn't go right to Navier-Stokes or something. Yeah, we started small, and so let's keep let's keep us a bit humble and start a bit smaller here as well. Yeah, and this is what we essentially looked at. And I mean, those familiar with fluid dynamics see these equations immediately. The first, really most easy thing to start with is the advection equation. So we're basically looking at a flow field and looking how does a property propagate in that flow field, but nothing more. Yeah. Then we add some nonlinearities, so some viscosity in there, and we are coming to the Burgers equation. First, we do it in 1D. Then we can do the same thing in 2D, yeah, which is then already becoming kind of relevant. It's kind of something we can touch at some point. And then the next step afterwards is going to the Euler equations, which are basically the backbone of today's aerodynamic simulation already, because we're conserving their mass, momentum, energy, and so on. And we are looking at compressible flows and can already look at high speeds. So going these steps is meaningful in looking at physics-informed neural networks. And if you're interested how we put it in on a quantum computer exactly, then just stay on the line, and in a few minutes from Pascal, Smith will present that. Just summarizing, yeah, so why applying quantum computing to aerodynamics problems? It's formulating different, yeah. Today, aerodynamic simulations are super computational demanding, and we're looking for a way to further scale in future for optimizing widely. Yeah? So we're looking at scalability, we're looking at also efficiency. And of course, we want to be looking for making use as much as possible already of today's hardware, looking at hybrid workflows.